Hey guys, welcome back. What we're going to be doing in this video is showing you how some mathematics can relate to the Rubik's Cube or any type of a 3D puzzle. Unfortunately, I don't have very good video editing skills, and I hope your favorite type of video, as Uncle Roger would say, is amateur. But let's get started. We're going to be using alg.cubing.net and Desmos just to show a couple quick ideas. And I'm going to start off with this idea that most people know um, called sexy move. R, U, R prime, U prime. You'll notice when we do a move like this on the cube, R, U, R prime, U prime, we are doing an R move and then we are inverting the R move later on. And you might say, well, does the order of it matter? And it does matter, because if we just did R, R prime, U, U prime, we would just have a solved cube again. But if we undo the R after we do a U move and follow it up by a undo of the U move, something special happens. We get some type of pattern. And you'll notice specifically this block in the top right corner and the block in the bottom right corner did switch spots. This one used to be blue, red, yellow, and this one used to be red, blue, white. So one would expect, if we were going to do this again, the same exact move, those blocks would change positions again. And you'll take a look, notice they do change positions. So what I'm getting at here is, if you do the same thing on a cube, algorithm wise or operator wise, the same thing's going to happen. Just like in mathematics, if you add 2, you should have some expected result. And if you add 2 and then subtract 2, you should have some expected result. And we want to look at these turns and rotations more so as mathematical operators. We can't really say they're addition, subtraction, multiplication, and division, but this is a whole different type of number system if you take a look at this cube. And you'll have to excuse my keyboard as I do this. Like I said, amateur video. Uncle Roger's going to obviously love this. So we're going to go to Desmos and take a look at some operators that you might find interesting, because I think you already know that if we take this algorithm and do it 6 times, if you're not into cubing, this might sound interesting. More of a math person, never took a look at a cube. If you do this algorithm 6 times, it actually goes back to a solved state. And most algorithms are going to do the same thing as well. I guess we'll take a look at this before we go to Desmos. Like if you do an M slice and follow it by a U, and then do the inverted M slice followed up by that. If you're if you're new to cubing, that would be an M slice right there. So I would expect, I haven't really thought about it, but I would expect if you do this 6 times, it'll get back to normal. Sorry, those auto firing keys from those video games. Oh, not 6 times, but this one turned out to be 5 times. And if you did something like MU2, M prime, how do we undo a U2? Well, you would have to do a U2 again, right? I would assume, I'm pretty sure this is 3 times. Most certainly is. Once again, M, U2, M, U2. The U2 undoes the other U2. Obviously, the M's undo the other M's. So there's a lot of patterns in cubes. You can take a look at this move called sledgehammer. People call it sledgehammer. R, F. R prime F, R, F prime. Did I do that right? R prime F, R prime F, R. Yeah, absolutely. And most certainly, if you do this one 6 times, it will repeat itself. Jeez. Yeah, absolutely. So you might say, well, that's great and all, but what if you do it with like numbers? How can we show this with numbers? Expected pattern. We're going to take a look at something on Desmos, and this is how I figured out how to solve a cube with no solution in front of me. If you take a number a, and let's just make a equal to 3 for now. We'll let it change later, and we let b equal, I don't know, 7, and we let c equal, I don't know, let's let c equal 15. Why not? We'll do the same thing. We'll do a move, another move, and then we'll undo the first move, and then we'll undo the second move. And we'll keep doing it, and we'll see if a pattern pops up. So let's take that initial A, and we will add in B. And we're going to multiply by C. So remember on this one where we did R prime and then followed up by R? So right here you have plus B. How do you cancel out plus B? Well, you would have to do minus B. And then in order to affect the entire thing, we have times C. So we would have to take this and divide everything by C. And you'll notice that we get a result of 6.7, etc. Now, it's not a very expected result right now, but remember, when we did this on the cube, we had to do it 6 times to get back to normal, or some type of like expected result. On a cube, there's only a finite number of combinations. It is like 4 quintillion or something like that. On a number line, though, there's a lot more. There's an infinite number. So what we're going to do is we're going to take the prior result, and we're going to do the same thing to it. We're going to take this. We're going to take that result, and we are going to add in a b. We are going to multiply it by c. We are going to cancel out the b with subtraction. Once again, if we do an r prime, we want to cancel out that r prime with an r. So if we do a plus b, we want to cancel out that plus b with a minus b. Multiplication by c, so we want to take the whole thing and divide it by c. And you'll notice we got another result. Now this is 6.98, etc. I'm going to take this again, and hopefully I don't bore you too much here, but we're going to do it again. We're going to do the same thing again. We're going to add b, multiply by c, subtract b, and then divide by c again. So we are going to do the operator of b, multiply that by c, subtract b, and then take the whole result and divide it by c. Now, how many times have I done this so far? We have done it 1, 2, 3. So why don't we do this 6 times? Why don't we do it 6 times? So we've done it 3 times. This is going to be time number 4, plus b times c minus b. Take the whole thing and divide it by c. We're going to take it again. 1, 2, 3, 4. This is the 5th one. We're going to add in b. We are going to multiply by c. We are going to subtract b, and we are going to take the whole thing and divide by c again. Once again, if you add b, how do you cancel addition of b? You have to subtract it. If you multiply by c, we have to divide by c later on. And one more time here, just for good measure, but I'm not going to put it below. I'm going to put it up here. And the reason why I'm going to put it up here is so we can take a look at it. We're going to take this fella, and once again, we're going to add b. We're going to multiply that fella by c, cancel out the b, and then divide all of that remaining stuff by c. And let's take a look at the result. We got 6.99999, etc. Now, that 6.999 is very, very close to b. What I'm going to do here is I'm going to press play on this a value. And I have not done this, but I'm almost going to expect that when I play this a value, that result is not going to change much, if at all. Nah, it stays right around 7. So I'm going to say if I followed this pattern of add b times c, subtract b by to somewhat undo the b value, and then divide by c to somewhat undo the c value, I'm going to get the same exact result as whatever the b is. I don't care what my a value is. I'm just going to pause it right here. Look at that, 6.9 something and 7. What if I play the C value? I'm going to almost expect the C value doesn't really change your result at all. You're going to get whatever B is. And sure enough, you look at that guy up there. Except for what? I saw a negative pop up. Saw some really goofy result. Now, why are you seeing very, very different results when you get to a certain point? We're seeing very, very goofy results as we get into numbers below 1 and above -1. My guess would be that if we are dividing by C here, if you divide by something like 0, we get undefined answers. So this works as long as C is not between a certain amount. And I guess if you really wanted to talk about this, we'd be talking about like a Taylor series. But once you get to a certain point, I think we get expected results here. Yeah, absolutely. Our interval of convergence is pretty wide here. Our interval of convergence isn't an interval that closes in between two numbers. It's actually outside of two numbers. But I'm going to leave it right out here, and I'm going to press play on this B value. And whatever that B value is, it's changing that. Like if I stop it right here at 6.33, I'm pretty darn close to 6.33. And this is how you can talk about mathematics when you do Rubik's Cubes. You can build your own algorithms by simply saying, I'm going to turn this side and undo it somewhere along the lines. And at some point, I don't care what your algorithm is, it could be 15 moves long. As long as you keep doing the same exact algorithm and there's parts of it that undo the original moves, you're going to get the same exact pattern to pop up eventually. And this is what I found most interesting about these 3D puzzles. I'm going to try to make more videos on mathematics. I don't see very many Rubik's Cube videos about mathematics, and you know, I I made all those tutorials before, and I am not the best at tutorials, and I am not the best at speed cubing. And if you want to see a review, I would just look up a review from, the website that's selling it. And if you don't trust the website and say, oh, well, they're just going to say their cubes are the best anyway, yeah, I'd beg to differ. If you go to a Cubicle and Speed Cube shop, they are very critical of bad cubes that come out. But I know math very well. I know engineering very well. I'm a teacher and engineer by trade on the side. And I'm going to try my best to do something different this year with this channel. I hope you guys enjoyed the video. Hopefully it sparked your interest in mathematics and you see how this mathematics can somewhat relate to this cubing. Have a great night.